Welcome to AI Paper Podcasts, the show where we really get into the details of the latest AI research papers. Today we're tackling a big one, OmniGen2, unifying multimodal generation with decoupled pathways and reflective capabilities. This paper introduces a pretty exciting open-source generative model. Seems like it's pushing the envelope for unified AI.
Oh, absolutely. And OmniGen2, it's not just some small step forward. It really is this versatile powerhouse. It can handle quite a range, high quality text to image, sure, but also really sophisticated image editing and impressively consistent in-context generation.
And the core idea, the real innovation, is this unique architecture.
Exactly. It uses two totally distinct decoding paths, one for text, one for images, and crucially, they have unshared parameters. That plus a decoupled image tokenizer is sort of the secret sauce.
Right, and it's not just clever on paper. The results seem pretty solid. They're hitting competitive performance on benchmarks for text to image editing.
Yeah, and doing it with a relatively modest parameter size, which is definitely worth noting compared to some other big models out there.
And there's this new benchmark too, Omni Context.
That's right. They developed Omni Context specifically for evaluating in-context generation. It's tough. And OmniGen2, it gets state-of-the-art consistency among the open-source models on this new standard. That's a big deal.
Plus, the open-source contribution sounds massive: models, code, datasets, even the data construction pipelines. That's pretty generous.
It really is. It sets up the community for future research in a big way.
Okay, let's dig in a bit deeper then. We've seen this huge push toward unified models, right? Moving away from having one model for text to image, another for editing, trying to get these powerful integrated systems.
Definitely. The field's been heading that way.
But unified hasn't always meant, well, better across the board, has it? What's the fundamental problem OmniGen2 is trying to fix that maybe earlier models, like the first OmniGen, or even some of the big names like Gemini or GPT-4o, kind of stumbled on?
Well, you've put your finger right on it. Those earlier unified models and others like Chameleon, Emu3, Janus, they've all made progress, no doubt. But they often have limitations.
Like what specifically?
Sometimes it's the range of tasks. Great at text to image maybe, but then falls down on tricky editing tasks. Or, and this is a big one, they struggle with consistency.
Consistency meaning? Like if I give it a picture of my dog and ask it to put the dog on the moon, it might change the dog's breed halfway through?
Sort of, yeah. Or, more subtly, maintaining the exact identity, the look, the feel of a subject when you're generating it into a new context based on an input image. Precise image editing also needs that consistency, changing one thing without messing up everything else. That's been a real challenge.
Okay, so it's hard to make one model do everything well and consistently.
Exactly. And the key insight from the OmniGen2 paper, the observation they make, is that simply sharing parameters between the text and image parts, like trying to initialize the image generation side with parameters that were optimized for language well, it just doesn't work that well.
Why not? Seems efficient on the surface.
It seems efficient, but parameters tuned for understanding text structure and meaning aren't necessarily the best fit for modeling the spatial and textural complexities of images. When you force that sharing, you often see a drop in image quality or consistency.
Gotcha. Like trying to use a grammar expert to paint a landscape.
Yeah.
Different skill sets.
Precisely. So OmniGen2 was really designed from the get-go to deliver strong performance across a wide set of generation tasks, specifically avoiding those compromises that come from naive parameter sharing.
Okay, that makes a lot of sense. So architecturally, how do they actually achieve this? This is where the decoupled pathways idea comes in, right?
Yes, exactly. This is the core architectural innovation. Instead of forcing parameter sharing, OmniGen2 uses distinct separate pathways. There's an autoregressive pathway for text tasks, handled by a multimodal large language model, or MLM.
Like a Quen model, I think they used.
That's right, Quen 2.5 VL3B as the base. And then there's a diffusion-based pathway specifically for image generation, the crucial part. The parameters for this diffusion model are randomly initialized and are not shared with the MLM.
So completely separate weights for the image generation part.
Completely separate for the diffusion process itself. This is a big departure from its predecessor, the original OmniGen, which, as they note, actually saw image quality decline when it tried sharing parameters with its text model backbone.
Interesting. So sometimes keeping things separate, even within a unified model, is the key. Specialization within integration.
If you put it that way, it's about letting each component do what it does best without interference.
Okay, so you have the MLM handling text and overall understanding, and the diffusion model handling pixels, but you mentioned VAE features earlier too. How do they fit in? Because getting fine visual detail right is often a challenge, isn't it?
It is. High-level encoders like the vision transformers, the VITs and MLLMs, they're great at semantics, understanding what's in an image, but sometimes they miss the really fine-grained pixel-level stuff.
Right, the texture of fur, the glint in an eye.
Exactly, those details. So OmniGen2 uses features derived from a VAE, a variational autoencoder, which is really good at capturing and reconstructing that fine visual detail. But here's the clever part. Those VAE features are fed only into the diffusion model.
Not into the MLM part.
Correct. They don't go into the MLM. This keeps the MLM focused on its core multimodal understanding tasks without getting, let's say, distracted by the low-level VAE encodings. It also avoids redundant image representations and keeps the architecture cleaner. They didn't need to extensively retrain the MLM just to handle these extra visual features.
So MLM for the what and where, VAE plus diffusion for the how it looks, pixel by pixel? Makes sense?
Pretty much, yeah. It lets each component play to its strengths.
Now, you also mentioned the MLM's hidden states being used. How does that contrast with other approaches, like using learnable query tokens?
Right. Some models use a fixed number of learnable query tokens to kind of summarize the visual information for the generator, but that approach can have limitations, like a fixed capacity. What if you have a really complex scene or long text? It can struggle.
So the number of tokens limits the detail.
It can, yeah. OmniGen2 takes a different route. It uses the actual hidden states from the MLLM, specifically from the layers processing the interleaved text and image inputs, as the conditioning signal for the diffusion decoder.
So it's tapping into the MLM's internal representation directly.
Essentially, yes. This provides a much richer, more detailed flow of information to the image generator without being constrained by a fixed number of query tokens. It scales better with complexity.
Okay, that's quite elegant. And then there's Omnero P. Cool name. The paper says it's crucial for consistency in things like editing. What is it, and how does it give the model that spatial awareness?
Omnero, yeah, it stands for Multimodal Rotary Position Embedding. It's really quite ingenious and fundamental to getting that consistency, especially for complex edits or in-context tasks. Think of it like a sophisticated coordinate system for everything the model sees, text or image.
A coordinate system?
Kind of. It has three main parts. First, there's ITSEC, the sequence and modality identifier. Every image gets a unique, constant ID. It treats the whole image as one semantic thing. Text tokens, meanwhile, just get the standard 1D increasing index, like normal row.
Okay, so it knows this is image 1, this is image 2, this is word 5.
Exactly. Then, for image tokens, you have two more parts. H for the 2D spatial height coordinate, normalized, and W for the 2D spatial width coordinate, also normalized. For text tokens, H and W are just 0.
So every image pixel effectively gets a 3D coordinate. Image ID, height, width.
That's a good way to think about it, yeah. And the combination is powerful. The H and W give it that fine-grained spatial understanding within an image. So if you say change the cat's collar, it knows exactly which pixels relate to the collar and which relate to the background that needs to stay the same.
Crucial for editing without messing up the rest of the picture.
Crucial, and the IDSEC helps it distinguish between different images or different instances of objects across images. If you say, take the cat from image 1 and the dog from image 2, the IDSEC helps it keep track of which is which. And the whole system gracefully simplifies to standard 1D positional encoding for text-only input. It's very flexible.
Wow, that's some clever engineering to handle position across modalities like that. So how do they actually train a system with all these moving parts? The frozen MLM, the separate diffusion model, this Omnero P.
It's a multi-stage process.
Yeah.
As we said, the MLM, the Qwen 2.5 VL3B, is mostly kept frozen. They only update a special image token that signals the start of image generation. This preserves all that pre-trained knowledge.
Okay, so the language and basic vision understanding stays put.
Right. The diffusion model, though, that's trained from scratch. They start with just large-scale text-to-image data to get the basics down. Then they move to a mixed task training phase, incorporating their high-quality image editing and in-context generation data.
The stuff from those special data pipelines.
Exactly. And then there's a final, really interesting phase, reflection training.
Yeah, the self-critique part.
Kind of. In this phase, they unfreeze all the model parameters, MLM included, temporarily. The model learns to generate an image, then generate text reflecting on that image's quality or alignment with the prompt, and then potentially generate or find image based on that reflection.
So it's learning to iterate and improve its own output.
That's the goal, yes. Learning to identify flaws and correct them.
Okay, you mentioned the data pipelines. The paper really emphasizes the data challenges, saying existing open source data sets, especially for editing and in-context stuff, just aren't good enough. Is that gap really that significant?
According to the paper, yes. They call it foundational data challenges. The idea is that the quality, consistency, and accuracy of instructions in many available datasets limit the performance ceiling for open source models compared to, say, large commercial ones that likely have access to better proprietary data.
So better data equals better models, essentially.
It's a huge factor, especially for these nuanced tasks. So the OmniGen2 team didn't just find data, they basically engineered it using AI itself. They built these really comprehensive data construction pipelines.
Okay, walk me through that. For in-context generation, where you need to reproduce a specific character or object accurately, how did they create that training data? Sounds tough.
It does. Their approach was really smart. They leaned heavily on video data.
Video. Why video?
Because a video naturally shows the same subject, a person, an object under different poses, viewpoints, lighting conditions. It's perfect for teaching consistency.
Okay, so how did the pipeline work?
It was quite involved. They'd extract keyframes, then use powerful models like Qwen 2.5 VL and grounding denode to identify and locate the main subject. Then something like SAM2 segment, anything model 2, to get precise masks and track the subject across frames.
So they're automatically isolating the subject.
Right. Then more AI magic. Filtering to ensure the subject is consistent, using another model, FLUX Part 1 Fill, to outpaint novel backgrounds, so the subject appears in new scenes, or inpaint to remove the subject from the original frame. Finally, a large VLM like Qwen 2.5 VL7B Instruct would automatically generate the detailed text instruction for the training example, like, generate an image of this specific dog sitting on a red couch.
Wow. It's like an automated data factory using multiple specialized AIs.
Pretty much. Figure 5 in the paper shows a nice visual of this multi-step process. They did something similar for in-context editing data too, using pairs of video frames with the same object, masking it, and generating instructions about editing one frame based on the object from the other.
That's incredibly thorough. What about general image editing data, like in-painting or changing actions?
Similar principles. For in-painting data, they addressed the common issue of bad instructions in existing datasets. They took high-quality text-to-image data, used an AI like FLUX Part 1 Fill again to randomly fill a region, and then, here's the clever bit, used an MLM to write the editing instruction based on comparing the original and the in-painted version. This ensures the instruction perfectly matches the visual change.
Instead of relying on potentially inaccurate human-written instructions.
Exactly. And for dynamic changes, actions, expressions, video data was key again. They developed methods to find pairs of frames from a video that showed local changes, like someone waving, but without major viewpoint shifts. Then again, a powerful MLM generated precise instructions describing that specific change. Figure 7 shows this process for finding suitable video frame pairs.
It sounds like the quality and relevance of the training instructions were a massive focus.
Absolutely. And then there's the reflection data pipeline you mentioned.
The self-critique data.
Yeah.
How did they generate that?
This was iterative. They'd start with some text-to-image data. The model generates an initial image. Then, a separate, powerful MLM they mention using Dubao 1.5 Pro acts like a critic. It assesses the generated image against the prompt, identifies flaws, like the prompt asks for 3 blue balls, but the image only shows 2 red ones, and then proposes corrections.
So the critic generates text explaining the errors and how to fix them.
Yes. And that whole exchange prompt, initial image, critique, suggested fix, becomes a data point for the reflection training phase. They can even do multiple rounds. Figure 13 in the paper shows an example of this iterative correction.
That's fascinating. Teaching the model not just to generate, but to evaluate and refine. Okay, so they built this sophisticated model and curated all this high-quality data. How did they go about proving it works? You mentioned the Omni Context benchmark. Why did they need to build a whole new benchmark?
Well, they argue that existing benchmarks for in-context generation were lacking. Things like DreamBench are okay, but often limited. And simple image similarity metrics don't really capture if the model followed the prompt correctly and kept the subject consistent, especially when dealing with multiple input images or real-world photos. There was a gap for a robust, large-scale evaluation.
So what does Omni Context look like?
It's large-scale, manually collected, and diverse. It includes personal photos, open-source images, animation stills, even other AI-generated images, a real mix. It's structured around 3 main image genres: character, object, and scene.
Okay, so different types of subjects.
Right. And then there are three main task categories: single input image, multiple input images, and scene-based tasks, broken down further into 8 specific subtasks, like generating a known character in a new pose or combining objects from different images. Figure 8 gives a good visual overview.
And how do they score the results? You can't just use CLIP score for something like this, can you?
No, definitely not. They use a hybrid approach. Human annotators help prepare the image prompt pairs, but the actual evaluation of the model's output is done using GPT 4.1.
Using another AI to judge the AI.
Yes, but in a structured way. GPT 4.1 assesses the outputs based on 2 key metrics: prompt following, PF, did it do what the text asked? And subject consistency, SEA, did it maintain the identity of the object's characters from the input images? Both are scored 0-10. They then calculate an overall score, which is the geometric mean of PF and SC.
And GPT-4 provides reasons.
Crucially, yes. GPT-4 provides detailed rationales for its scores, which make the evaluation much more transparent and trustworthy than just getting a single number back. Figure 9 shows examples of these evaluations with justifications.
Okay, makes sense. So the big question: how did OmniGen2 actually perform on Omnicontext and other standard benchmarks? Did the architecture and data pay off?
The results are genuinely impressive, especially considering its size. It strikes a remarkable balance across everything: visual understanding, text-to-image, editing, and in-context generation.
Let's break that down. Visual understanding first.
Solid scores. On benchmarks like MMBench, MMMU, MMVet, it performed well, leveraging that frozen 3 billion parameter Quen MLLM. The advantage is clear: good understanding without needing a massive, dedicated vision model, keeping things lightweight and efficient.
Okay. What about standard text-to-image generation? That's always a competitive space.
Very competitive. On Geneval, which tests understanding complex compositions, OmniGen2, a version fine-tuned on reflection data, hit 0.86. That's incredibly close to the state-of-the-art Bagel model, which scored 0.88.
Close score. Okay.
But here's the kicker. OmniGen2 achieved that with only 4 billion trainable parameters, compared to Bagel's 14 billion. And it was trained on way less data, 15 million pairs versus Bagel's 1.6 billion.
Wow, okay. That's hugely more efficient then.
Massively efficient. And on DPG Bench, which focuses on following long, detailed prompts, it scored 83.57, beating other unified models like Uniworld V1 and getting close to specialized text-to-image models like SD3 Medium. The quality is definitely there. Figure 10 has some nice visual examples.
Very impressive efficiency. How did it handle image editing? That relies heavily on consistency.
It really shone here too. Strong performance across several editing benchmarks like EmuEdit, GetItBenchN, and ImEditBench. On EmuEdit, for instance, it got the highest score for applying the edit effectively, CLE out, and was second best at preserving the unedited parts, CLPI DNO. That shows a great balance.
So it changes what you want changed and leaves the rest alone.
Ideally, yes. On GetItBench, it had the second highest semantic consistency score. They do note some weaknesses, like with portrait touch-ups or modifying text within images, likely due to specific gaps in their training data for those niche tasks. But on ImEditBench, it set a new state-of-the-art for open-source models. The video data training really seems to help with capturing dynamic actions in editing. Figure 11 shows off its versatility, changing expressions, colors, motion, adding, removing things.
It sounds like a true all-rounder.
Yeah.
So back to their own benchmark, Omni Context, for in-context generation.
It established a strong baseline there, with an overall score of 7.18. Compared to other open-source models, it showed clearly superior prompt following and, crucially, subject consistency.
Better than other open options. How about closed source?
When compared to top closed-source models, the paper notes GPT-4 was still better overall, particularly at prompt following. Another model, Flux.1 Context, showed slightly better subject consistency. But OmniGen2 holds its own and demonstrates a strong ability to understand a subject from context and re-render it accurately. Figure 12 has some compelling examples of this.
And the reflection capability. Did that training phase work in practice?
It showed definite promise. In tests, the reflection fine-tuned model could successfully look at its first attempt, identify issues based on the prompt, like wrong color, wrong number of objects, wrong shape, and then generate a corrected image in a second round. It even learned to stop generating when the task was done properly.
So, early signs of AI self-correction in image generation.
Exactly. It's a very promising direction. But it wasn't perfect.
Okay.
Yeah.
What were the limitations there?
They observed instances of over-reflection, where the model might get critical about simple prompts where it wasn't really needed, or draw incorrect conclusions. Sometimes it would generate a reflection suggesting a fix, but then fail to actually implement the fix in the next image, or even follow flawed reflection instructions.
So the self-critique isn't always accurate or helpful yet.
Not always. They attribute this mainly to the limitations of the 3 billion parameter MLM used for reflection and probably needing more higher quality reflection training data. It's still early days for that capability.
That makes sense. So stepping back from reflection, what other general limitations of OmniGen2 did the authors identify? Where does it still struggle?
They were quite upfront about several areas. First, there's a performance gap between English and Chinese prompts. English just works better currently.
Okay, language bias.
Second, it struggles to modify human body shapes accurately, which they think is down to not having enough specific training data for that kind of manipulation.
Data scarcity again.
Third, it's sensitive to the quality of the input image. If you give it low resolution or poor quality images for context or editing, the output quality degrades noticeably. Details get lost.
Garbage in, garbage out, to some extent.
Somewhat, yes. Fourth, when you provide multiple input images, it does better if the prompt clearly states the correspondence, like use the bird from image 1 and the desk from image 2. Ambiguity can trip it up.
Needs clear instructions for complex inputs.
And finally, even in context generation, it sometimes doesn't perfectly reproduce the object from the context image. They found that increasing the classifier-free guidance scale can help push it towards better fidelity, but it's not a complete fix. They suggest that scaling up the model size might be necessary to fully nail that perfect object reproduction consistently.
Okay, so still room for improvement, but it sounds like a really significant step, especially for open source. What's the big picture takeaway here? What does OmniGen2 mean for the field?
I think it's a major contribution. OmniGen2 clearly demonstrates that you can achieve highly competitive, unified multimodal generation across a wide range of tasks, text-to-image, editing, in context within an open source framework, and do it efficiently.
The decoupled architecture and the data pipeline seem key.
Absolutely. The architectural insights about not sharing parameters naively, the clever use of VAE features and MLM states, and Omnero P, that's important. But equally important are those comprehensive data construction pipelines and the new Omni Context benchmark. They're giving the research community not just a model, but also the tools and methods to build and evaluate better models going forward.
It really lowers the barrier for others to build on this work.
Exactly. It pushes the whole field forward, particularly in the open source domain.
So looking ahead, as we see more models like OmniGen2 blending sophisticated architectures with this kind of meticulously engineered data, it makes you wonder, how fundamentally will this synergy change our creative tools or how we interact with information visually?
That's the big question, isn't it?
And what happens when these models get even better at self-correction, at reasoning about their own outputs? What kinds of new applications might pop up when AI has that level of nuanced understanding and refinement? Something definitely to think about.
For sure. And the authors mention plans for scaling up the MLM and exploring reinforcement learning for reflection, so they're clearly pushing in that direction.
Well, if you want to dive deeper into OmniGen2 yourself, we definitely encourage you to check out the project page and the GitHub repository the authors have made available. There's a lot more detail there. That's all the time we have for today on AI Paper Podcasts. Thanks for tuning in.